At first glance, the idea of a particle moving faster than light sounds like science fiction, or worse, a violation of the fundamental laws of physics. After all, Einstein's theory of special relativity famously tells us that nothing can travel faster than the speed of light in a vacuum. This is the ultimate cosmic speed limit, a boundary that even the fastest particles in the universe cannot cross. So how can we possibly observe a charged particle emitting light because it is moving faster than light? This is not a thought experiment. It is a real glowing blue phenomenon called Cerenkov radiation, and it presents one of the most intriguing paradoxes in modern physics. The key to resolving this paradox lies in understanding that the speed of light is not always the same. While the speed of light in a vacuum, denoted c, about 299,792,458 meters per second, is indeed the universal maximum, light travels more slowly in materials like water, glass, or even human tissue. When light passes through these media, it interacts with atoms and gets scattered and delayed, reducing its effective speed, sometimes by more than 25%. So, although nothing can exceed c, particles can travel faster than light does within a specific medium. This is not breaking the laws of relativity, it's exploiting a loophole written into them. Now imagine a high-energy electron entering water at a speed greater than the local light speed in water. Suddenly, it's in a situation analogous to a sonic boom. Just as an aircraft traveling faster than the speed of sound creates shockwaves in air, this electron creates a kind of electromagnetic shockwave in the medium. The result? A cone of glowing blue light, Cerenkov radiation, emitted at a specific angle determined by the particle's speed and the optical properties of the medium. But how does the radiation itself form? As the charged particle speeds through the medium, it polarizes the molecules along its path, pushing their electrons slightly out of alignment. These molecules rapidly return to equilibrium, and in doing so, they emit photons. If the particle moves slower than light in the medium, the disturbances cancel out, and there's no coherent radiation. But when the particle moves faster than the phase velocity of light in that medium, the emitted photons constructively interfere in a conical wavefront, creating the signature Cerenkov glow. So, is this a violation of special relativity? Absolutely not. The particle never exceeds c, the speed of light, in vacuum. Instead, it exceeds the speed of light in that specific medium. Relativity remains fully intact. What's more, the particle loses energy as it emits Cerenkov radiation, slowing down as it continues to interact with the medium, much like how a supersonic jet experiences drag. This radiation is not free, it's a toll paid for pushing the boundaries of speed in a dense environment. Where does this phenomenon show up? One dramatic example is in nuclear reactors, where fast electrons from radioactive decay move through water faster than light can. The result is the famous blue glow seen around reactor cores, a kind of continuous Cerenkov light show. It's also used in particle detectors, like those in neutrino observatories and high-energy physics labs. When particles such as muons, electrons, or neutrinos pass through a detector medium, like heavy water or ice, the Cerenkov light can be captured by photomultiplier tubes and used to reconstruct the particle's trajectory and speed. The paradox extends intriguingly into astrophysics. Cosmic rays traveling through the Earth's atmosphere at near-light speeds can emit Cerenkov radiation as they encounter denser air molecules. Special telescopes on Earth observe these brief flashes of light to study the origin and nature of these high-energy particles. There's even a speculative twist. Could we use Cerenkov radiation to detect violations of known physics, such as faster-than-light particles or exotic media with strange optical properties? So far, no evidence has broken the cosmic speed limit, but researchers remain vigilant. The consistency of Cerenkov radiation with both quantum theory and relativity makes it a powerful probe of the fundamental structure of space-time. So how can a particle emit radiation by moving faster than light without breaking the rules because it's not exceeding the universal speed limit, only the local speed limit of light in a material? Like a supersonic jet outrunning sound, the particle carves through the medium, leaving behind a glowing footprint of its passage. The Cerenkov Radiation Paradox is not a contradiction, it's a beautiful demonstration of how physical laws adapt in context, reminding us that light, while fast, is not always the fastest in every situation. Could this paradox, far from being a flaw, actually be a window into new physics, new detectors, or even new forms of communication? The luminous blue trails left behind in water and space suggest that the answer may indeed be yes. Cerenkov radiation occurs when a charged particle travels through a dielectric medium at a speed exceeding the phase velocity of light in that medium. This process results in the emission of electromagnetic shockwaves that form a characteristic conical light pattern. Importantly, the particle never exceeds the speed of light in a vacuum, but merely the reduced speed of light in the medium due to its refractive index. Thus, the phenomenon is entirely consistent with special relativity, as the universal speed limit c is never violated. Example, high-energy electrons traveling through water emit a vivid blue glow, Cerenkov radiation, without ever exceeding the cosmic speed limit in vacuum. Analogy, it's like a speedboat creating a wake when it moves faster than the water ripples on a canal. Even though the boat's speed remains within its overall maximum limit, the cosmic speed limit defined by special relativity applies to the speed of light in a vacuum, c, not to its slower phase velocity in a medium. In a medium, light's effective speed is reduced by the refractive index, allowing particles to exceed this local light speed without breaching fundamental laws. This key distinction permits charged particles to induce Cerenkov radiation while remaining subluminal relative to c. Consequently, the apparent superluminal motion is a local effect tied directly to the medium's properties. Example, an electron in a plastic scintillator can travel faster than light does within the plastic, yet remains well below c. Analogy, it's like a car driving faster than the speed limit on a narrow, winding road while still obeying the overall speed restrictions of the highway system. As a charged particle exceeds the phase velocity of light in a medium, it polarizes surrounding molecules, which then relax by emitting coherent photons. This constructive interference forms an electromagnetic shockwave, radiating outwards in a cone whose angle is determined by the particle's speed relative to the light speed in the medium. The emission process is a direct consequence of the wave nature of light and the interference among its lower frequency components. The result is a distinct measurable light emission without any violation of energy or momentum conservation. Example, in nuclear reactors, fast-moving electrons produce a blue glow in water due to the conical emission of Cerenkov radiation. Analogy, it's like a supersonic jet producing a sonic boom. Even though the jet doesn't defy speed limits in open air, it creates a shockwave because it's moving faster than the speed of sound locally. The production of Cerenkov radiation adheres strictly to the conservation of energy and momentum, where the charged particle loses a fraction of its kinetic energy by emitting light. This energy loss is accounted for in the slight deceleration of the particle as it travels through the medium. The emitted photons collectively carry away the energy difference required to balance the equations of motion. Despite the local superluminal effect in the medium, the overall energy budget remains fully consistent with established physical laws. Example, particle detectors utilize the measurable energy loss from fast electrons observed as Cerenkov light intensity to infer particle energy. Analogy, it's like a cyclist who emits a small burst of energy as a shout while riding, resulting in a negligible but measurable slowdown that adheres to energy conservation. The refractive index of a medium quantifies how much the speed of light is reduced relative to its vacuum speed, c. A higher refractive index means light travels significantly slower, thus lowering the threshold for a charged particle to exceed that speed and emit Cerenkov radiation. This dependency directly connects the intensity and angular distribution of the radiation to the optical properties of the medium. Therefore, understanding the medium's refractive index is crucial for predicting and controlling Cerenkov emission. Example, water with a refractive index of about 1.33 reduces the speed of light sufficiently so that even moderately fast particles can trigger Cerenkov radiation. Analogy: it's like running on a treadmill that slows down the moving belt, allowing you to outpace it even though your running speed never exceeds your maximum capability on flat ground. Cerenkov radiation exhibits a continuous spectrum that is more intense in the blue and ultraviolet regions due to the frequency dependence of the emission intensity. This spectral signature is a powerful diagnostic tool in particle physics and astrophysics, where it aids in identifying high-energy particles. Specialized photodetectors and spectrometers are employed to capture and analyze these spectral features, revealing details about the particle's speed and energy. The spectral profile confirms that all contributing frequencies are within the band-limited range set by the medium, even if locally the oscillations appear faster. Example: the blue light emitted in nuclear reactors is analyzed with spectroscopic equipment to determine the energies and velocities of the incident particles. Analogy: it's like using a prism to break sunlight into its constituent colors, where the observed blue hues reveal information about the conditions under which the light was produced. Cerenkov radiation is widely exploited in experimental physics and medical imaging due to its distinct emission pattern and spectral properties. Large water or heavy water tanks serve as Cerenkov detectors, capturing light from high-energy particles such as neutrinos and cosmic rays. In medicine, Cerenkov luminescence imaging uses the phenomenon to track radiopharmaceuticals in vivo, offering a non-invasive diagnostic tool. These applications leverage the reliable, quantifiable properties of Cerenkov light to advance both fundamental research and clinical practice. Example: the Super Camo Kande detector in Japan uses a vast tank of water to capture Cerenkov light from neutrino interactions, enabling the study of rare astrophysical events. Analogy: it's like using a giant, highly sensitive camera that captures a distinctive flash whenever a speeding particle passes through a darkened room. The paradox of Cerenkov radiation lies in its counterintuitive nature, where a particle appears to break a speed barrier locally while never exceeding the fundamental speed limit in vacuum. This challenges simplistic notions of signal propagation and compels a nuanced understanding of phase versus group velocity in wave phenomena. The theoretical models rely on precise interference effects among lower-frequency components to explain the localized superluminal oscillations. Ongoing research aims to refine these models and address challenges in measuring and harnessing the subtle features of Cerenkov radiation. Example: advanced simulations of Cerenkov emission help optimize detector designs by predicting the exact cone angle and intensity distribution of the radiation based on particle speed and medium properties. Analogy: it's like using complex choreography to create a visual illusion of speed that seems to defy the rules of the dance floor, while in reality, every move is perfectly within the bounds of the music. The paradox is resolved by recognizing that the faster-than-light motion in a medium refers only to the particle's speed relative to the reduced phase velocity of light, not to the ultimate speed limit c in a vacuum. The superluminal condition is a local effect driven by the medium's refractive properties, and it results in electromagnetic shockwaves rather than a violation of relativity. Energy conservation, causality, and Lorentz invariance remain intact because all measurements are ultimately referenced to the vacuum speed of light. In essence, Cerenkov radiation elegantly demonstrates that local superluminal phenomena can coexist with universal relativistic constraints. Example: in experimental setups, electrons generate Cerenkov radiation in a medium like water while their speed remains significantly below c, in full agreement with theoretical predictions and relativistic principles. Analogy: it's like a boat speeding ahead on a narrow canal where the water flows slower than the boat, creating a bright wake, yet the boat never exceeds its maximum speed on open water.